I'm Liz Milićević. I can say, actually, that was the best job that anybody's done on saying my last name in an introduction. But I'm Liz Milićević, and I'm from Haverford College, for those who didn't hear. Thanks so much for rejoining after lunch. So let me share a bit about my, and I'm going to steal Oliver's term, philosophy with you. So I have a philosophy that guides every single paper that I've ever written, but you might not recognize that it does. Sometimes it's in the background, and a lot of times it's in the foreground. And an example of an application of this philosophy is some Schubert calculus, which I will explain. But there's other things you can do, and I'll hope to be able to say a little bit of that about those kinds of things as well. So, so the large bulk of the talk will be focused on setting up the philosophy and explaining the toolkit, and then we'll do some applications once we're prepared. So the applications that I'll talk about span joint work with Kaisa Taipale in one project and Petra Schwer and Ann Thomas in another. So I'll try to be careful along the way of whose is whose. Okay, but here's the philosophy. And I had the word already tucked in even before Oliver spoke. So if we're interested in studying flag varieties, which is my hypothesis if you're present in this room, that it is often fruitful to carve them up into orbits of convenient subgroups, and your choice of subgroup will be dictated by the problem that you want to attack. And to describe the structure of how those orbits, to describe their structure, for example, how certain orbits meet one another, whether they do, whether they don't, these kinds of questions. And the punchline of the talk is that if that is a structure that is present in a problem that you look at with respect to flag varieties, namely that you're looking at certain orbits, carving your flag variety up into certain orbits and wanting to study their structures, that you really are looking at a sequence of pictures like this. And I'll call these folded alcove walks. And so the first large bulk of the talk is actually just going to be to explain these pictures. And then we'll solve various problems using those pictures in specific ways. All right. So that's both the philosophy and the summary. Probably you've encountered this notation already, especially if you've been here for the duration, including the summer school. So I'll need to fix a group for this talk. It'll be a reductive group over the complex numbers, although I like to work with a lot of different fields, including positive characteristic in various other applications. Fixing a Borel, which I'll denote by B, and its opposite, which I'll denote by B minus when needed. And for me, W will be, and I'll emphasize the word finite, Weil group. So that's some quotient of the normalizer of the torus, but if you'd like to be concrete, just think about these examples. So for G equals GL3, say you could take B equals the upper triangulars, and the torus inside would be the diagonal matrices. The opposite would be to be opposite of upper and be lower in this example. And then the Weil group for this particular example is the symmetric group. So I've just written down an example of a permutation matrix. I'm being sloppy with signs, but yeah, so don't press on that. Okay, so here's a definition of the flag variety. So the flag variety, for me, though, I will often say this is the finite flag variety, is to look at a certain quotient, so G mod B. So you're looking at complex entries inside of whatever group you choose, say, for example, GL3 in the favored example, and you're forming a quotient by those, say, upper triangular matrices. And so you have a set of cosets, like algebraically. That's a way to think about the flag variety. That's like not algebraically, that's like a not very productive way to like work with it, but it is a definition. And it's the right definition to get us into the pictures that I showed you. And so, for example, that flag variety, so this set of cosats, decomposes into various Schubert cells. I mean, really, you need to take a quotient here to pick your flag variety apart in this way. And you could do various things. So you could look at B double cosats, or you could look at B minus orbits of B cosats. And both of these flavors of a Bruja decomposition that I've written down here are indexed by that same exact group, that finite Weil group, or just the symmetric group Sn, if you're thinking about the GL3 example. Well, S3, if you're thinking about the GL3 example. Okay. So your group will admit various Schubert decompositions. Okay. So I'm going to force you to think about those Schubert decompositions in what I think is probably a different way than people have forced you in the summer school, certainly than in other talks in the conference so far. And so I'm going to actually start with the basics and force you to think about the symmetric group S3 in a very specific way, okay? So to me, here is S3, and this is like the only way I ever think about S3, essentially, at least in the background. So that I'm highlighting the group S3 here, and what I've done is I have a bunch of hyperplanes in this plane, which I've drawn, and where those hyperplanes get drawn and what angles they are to each other, et cetera, is completely determined by the group that I pick. Okay, so I've drawn them in the SL3 way, and what I've done is between two adjacent little, so here's two hyperplanes which meet here, and then I've shaded a cone here, and I've colored that yellow. I'm going to think about that as the identity of my group, the identity of S3, just the symmetric group S3. I'm going to pick out 6 elements for you. There's the identity. It's shaded in yellow, and it's that triangle, or cone if you wish. But the one presentation for the symmetric group S3 is that it's generated by 2 reflections. So S1 and S2. These are what you think they are. S1 swaps 1 and 2, and S2 swaps 2 and 3. So they are the simple transpositions, the usual Coxeter generators that you're probably used to playing with. What I will do is actually flip across one side and call this cone now S1, and if I do the other reflection, then I will call this cone S2. And now I can compose doing those 2 simple generators one after the other, and I get the labels of the other 6 regions carved out by those hyperplanes. So for example, if I first do S1, I'm here, and if I then do the S2 flip, I'm down here. So that's labeled by S2, S1 because I'm thinking about SI acting on this space, acting from the left. So if I do S1 first, it comes first that way. And then I did S2, and I write it down in the opposite order that you would read, function composition order, right? So there's the symmetric group, S3. These 6 regions, these 6 triangular or cone regions in the plane, okay? So that's a picture of S3. And okay, before I say more, okay, I don't want to, don't look too closely yet. I want to make sure, because I gave this talk once more. In fact, apologies to those of you who have seen it recently, but I gave this talk once more before, and I realized that one point was lost. So I want to say it now, is that if all of your favorite problems live on the finite flag, the exact G mod B that I just defined, this story still completely works. You just look at a piece of the pictures that I'll draw you instead of all the pictures that I'll draw you, and I can try to articulate that difference along the way. So I'm about to, you got a sneak preview, I'm about to actually take the finite flag and then build up the affine flag variety out of it. But if you're not an affine person, it doesn't matter. The philosophy still applies. And your pictures will just be concentrated in sort of smaller pieces of the story that I present to you. It's still all kind of, it just works just the same. Okay. But you get lovely pictures if you allow me to draw things in the affine setting. So for the purpose of this talk, let me define this particular affine context, although there are others one could choose. So I will now, instead of just working with matrix entries in C, I'll actually jump up and get Laurent series. So what I have, it's easier if I say what's here. So this double bracket is Laurent polynomials. So I have series. So t is a variable, and I can have powers of t, and those can go as high as you want, including forever. In this larger field F, here we go, in this larger field F, I can have negative powers of t, that's allowed, but I can only have finitely many of those with non-zero coefficients. So I get a little bit of negative power of t. A possible here, series, but no negative powers here. This is the ring of integers inside of this discretely valued field, whatever. This is the units inside of this DVR. But what they are concretely is that I have to have a constant term and then like higher. Okay. Okay, so I've just defined for you a field and some other like pieces of that field, some rings inside of that field. Now I'm going to define for you the analog of B. Okay, so I'll tell you what it is, and then I'll tell you what it's not. But your life gets interesting if you try to do what it's not. So so the Iwahori subgroup is going to play the role of B. So I'm going to define a flag variety for you. It's going to be G mod something, and that something is going to be this I. Okay. What you might guess is you just take upper triangulars again, or something like that, right? And that guess, you can actually build a really interesting flag variety out of that. You build the periodic or semi-infinite flag in this way, and that's a lot more complicated to study, but people do, and increasingly many people, even including people in this room, are doing that. But sort of the most direct analog of B does this. So instead what you do of the like just take upper triangular is you take, there we go. You take, you look at this projection. So first you only look at power series entries, and then you project where you just kill off the variable. So t is getting sent to 0, and then you ask, what became upper triangular? So it's the pre-image of the upper triangulars under this like send t to 0, kill off t projection. And so as an example, just a super small example, but it's enough to get the point, here would be I in the case if G were SL2. So we're just looking at 2 by 2 matrices. I'm only looking at these like power series entries. So B, this upper piece, that can be whatever it wants, but the lower piece has to come, it can't have a constant term, because when I project, when I send t to 0, I need to see something upper triangular. So I need that lower corner, this little c, I need it to vanish when I kill off t. So that requires, by this definition, that requires that c is coming from a particular ideal. So not, yeah, has to have t and higher stuff. And then whatever just conditions of the group force me to be picking stuff out of the, the units on the diagonal in this case. Okay. And then you have another flag variety that you can define in exactly the same way, just as a quotient, G mod I instead. But when I say G mod I, and I may stop saying always G of F mod I, so when I say mod I, I'm in the affine context, so I'm up in that Laurent series situation in terms of entries in order to form that quotient by I, which has a bunch of Laurent series stuff inside of it. So hope that won't be confusing. So I've built a different, much larger flag variety for you. Just as cosets, that's the definition. But the philosophy of what we did in the finite case carries over in the affine case. In particular, there are Schubert cells still. And they look like you just sort of copy and paste exactly what you had. I mean, these are some types of Schubert cells, some examples of Schubert cells, but these are the parallels of the Schubert cells I showed you for G mod B. I double cosets, or how about I minus orbits inside of this G mod I? And let me not define I minus for you right now, although I could if you care, if you need, but you won't need for this talk. So yeah, oh right, but what I actually really want to pay, I want to pay special attention to is how to think about this indexing subgroup. So what is indexing my Schubert cells in the affine case is now something that's also called the Weil group, although it's called the affine Weil group, and I'll be able to say exactly why it has that name. And so it's an infinite group, so I have infinitely many Schubert cells in this game. And, but I have the same exact way to think about those visually as I did and showed you for S3, for the finite flag, for the finite Weil group for GL3. All right, so let me show you that. Just for kicks, if you like to work in type C, whoop, SP4. That's a good reminder for me to say, I'm open to all types, because everything that I tell you, you just draw your hyperplanes at slightly different angles and you do the same exact thing. So to me, the combinatorial obstructions are not really any different, type A to type C to type G. I love G2, woo, yes. Yeah, so this is like just an opportunity to like show you that you can play around in all types in this way. Okay, so slightly different angles here between the red and the blue than I had in the case where I was showing you S3. This is the SP4 configuration of those red and blue, but still getting the generators S1 and S2 kind of in the same exact spots. I've now, instead of writing 1, I've written fancy, whatever, MathCal A0. This is 1, okay. To me, it's the base Alcove, so I have to call it A something, but I'll say that shortly, formally somewhere, I hope. So this is the origin, which I've now like made a note of, where these two, the red and the blue, where they meet. This is like 0, like literally the vector 0 in the plane, 0, 0. And all I'm gonna do is just drop in one more hyperplane, and that's the green. Here we go. The greeny hyperplane has dropped in, and allow one more reflection across the green. That's now allowed as an element of the group. Note that this is my linear algebra students' favorite way to prove that something is not a linear transformation is that 0 moves. If you're lucky, that's enough to look at that and get a true-false question correct. So yeah, so 0 moves if we reflect across that green line. So in particular, we're leaving the world of linear transformations, but we've passed to the world of affine transformations. Everything, all the compositions of all of these will be affine transformations in plane, and that's where the word affine comes from. So I have one additional generator. And then what happens is a little more interesting. So now I've shaded in a triangle which I will identify with the element S0 in this group. And if I, after the fact, do the reflection across the red, so I'm doing the S1 reflection, then I identify that resulting new gray triangle up top with the element S1 times S0, written in the same function composition way as before. And then I just like keep doing this. So just for, the joy of using all the colors, I have now also applied this blue reflection across the S2 type of reflection. So I now have a gray triangle down here, which is identified with the group element S2, S1, S0, and so forth. So if you do this in all possible ways, all of these reflections composing the S1, S2, and S0 in all possible ways, you tessellate the plane by these particular right triangles. That would be the result. And so these gray right triangles are, to me, the affine Weyl group elements corresponding to the group choice, G equals SP4. And I'll just always call one of these triangles, to me, will always be called an alcove. All right. So we had, we secretly had alcoves before when we looked at S3. Now we have like more alcoves looking at our Schubert cell indexing set for the affine flag. And that's what we have so far. So we can think about a Schubert cell now in either the finite or the affine flag variety. Okay. And to study the affine flag variety, we could use the same philosophy. Here I'll just like call out a name. So if you happen to be choosing the exact two kinds of Schubert cells that I showed you before, then, and looking at where they meet, you're getting affine Richardson strata. And these are also following the same punchline, and looking at intersections of those kinds of Schubert cells is giving you these pictures, folded alcove walks. Now you see a bunch of alcoves, at least, that's coming together. I have to tell you how to walk through alcoves, and then fold. So here's how we take a walk. This is the same G equals SP4 picture. So here's my origin, and here's the identity alcove. I am now labeling this picture slightly differently than I had in the previous pictures with the red and the green and the blue hyperplanes, because I'm actually labeling the edge of every single alcove with a 1, a 2, or a 0. And it doesn't like follow exactly, maybe always. Well, anyway, I'm just doing it, let me just say, I'm just doing it in a very specific way. I just want to capture the action on the other side, on the right, whatever. Okay, so I'm just labeling the edges here, always with a 1, a 2, and a 0. Each alcove has a unique 0 side, a unique 1 side, and a unique 2 side, and they're completely determined. That's, for us, maybe that's enough to say. Okay, and so I'm just going to take now a walk. A walk just means like cross orthogonally, like a hyperplane, going from one alcove into an adjacent next one. So ping, ping. Sometimes I'm like lumping a few steps together. If you wish to, if you do this labeling, you can actually track now in the reading order. You can track like this way what word corresponds to the place where you end up. So let me see if I can do this right. So I cross a 2 edge, a 1 edge, a 2 edge, a 0 edge, a 1 edge, a 0 edge. Yeah, there we go. 2, 1, 2, 0, 1, 0. So I'm just, now I have a way of writing down the word in the way we normally think of things. Okay, so I'm just walking from one alcove to an adjacent alcove. That's all that's happening. I can label things so that I can pick out a word along the way, if needed. Okay, so my claim is that in every alcove walk that you do like this corresponds to a single coset inside of the affine flag, G mod I. So a point little xi, where the little x is the element that labels where you end up. So yeah, that's all. So this walk represents a single coset, this single coset. It's this element, 2, 1, 2, 0, 1, 0, I in the affine flag. That's a picture of a single coset. If I do something, it seems like it's like a phantom thing to do, but whatever. If I pretend now that each step along the way is labeled by a parameter, these parameters, I hope I said where, yeah, these parameters are coming out of C. So these parameters are coming out of wherever your coefficients for your Laurent series are made of. They're not as huge as living in the Laurent series world themselves. They're just complex numbers. So if I parameterize each step along the way, this is now a perfect picture of the entire double coset, IXI, I claim. So just allowing those parameters to like walk through all possible, oof, walk is a bad word, like range, vary through all possible complex numbers actually fattens this picture up and captures the double coset IXI. Mark. Yeah. Oh, okay. You reminded me to highlight a word I have on the slide and didn't say out loud, which is important. Let my walk be minimal, meaning don't like go crossing a whole bunch of hyperplanes unnecessarily and come back. Yeah? But if you go around, so you have to pick a walk per x. And then, yeah, then you get like that double coset one time. But it doesn't matter which choice you make. Yep, different parameterizations of the same cell. Yep. Yes, they do. Yes. Yeah. Yeah, all of this stuff is like Steinberg 67 or something like, I mean, it's nothing. Yeah, exactly. It's just coming from picking apart all of these groups, in particular right now, the Iwahori, into a product of its one parameter subgroups, absolutely. Yep. Okay. All right. Okay, so walk to an x. In your mind, imagine they're labeled by some parameters, but don't think too hard or deep about it. So walk to an x and you get one Schubert cell. That's the punchline so far. How do you meet another? How do you meet another Schubert cell? So that's the thing I have to explain now. So for that, I'm going to start to be able to fold these walks, and I just need to give you rules about how this folding is permitted. All right, so we're going to have an orientation induced by, well, in general, it could be induced by so many things. I've thought about all of them, I think. But for now, an alcove could be a way of inducing an orientation. And so here's the way I like to think about it. So we're happy when it's sunny, so except it's really hot right now. Yeah. But anyway, in general, okay, great. Beach time is happy. We're happy when it's sunny. Place the sun in the middle of an alcove, and everything facing that sun is positive, because positive, happy. Facing the sun, happy time, positive. So that's how I've labeled this picture, right? So the yellow, think about this yellow as the fundamental alcove, as the base alcove, as the identity element of the group, the starting point for all my walks. Okay, that's what this yellow is. Put the sun in there. Then this hyperplane, for example, is positive over here, but negative here and negative here because it's facing away on the negative side, and so forth, right? So this is an orientation that I'm choosing just to show you certain applications, but you can do like lots of different stuff. Yeah, so now essentially the only rule is we're gonna be permitted to fold an alcove walk, but you can only fold on the positive side. If you fold on, if all folds that occur on positive sides of a hyperplane, we call the walk positively folded. Let's look at some examples. And I think maybe here is a good example where I can just show you that. So this is where my walk is starting from. Sun is here, inside, right there. That's the sun right there. So if I look all the way down here, here's a fold that has happened. I'll tell you like algorithmically how to fold in just a second. But just notice that I have a fold that occurred here. And look at this hyperplane. Here's my sun. So this is on the positive side. Okay, that would be a positive fold that I've just illustrated. This one is too. That's a positive fold right there, because it's shining towards the sun. So these walks are trying to like get sunnier. Right? Yeah. Okay, and so you're only allowed to do positive folds, and once you've made a choice, you can't go back. So this is actually coming from the underlying root subgroup shenanigans, the Steinberg relations in the group, is that I have to make a decision. Am I going to fold here, yes or no? And then once I've said no, I can't go back later and change my mind and be like, oh, but I wanted to fold at the beginning. So once you've made your choice, are you folding here, yes or no? You've made it, and you can't change your mind later. So here's an example of folding a walk. And I've smoothed it out in the beginning. So here's my original minimal walk. And I am preparing to fold against this hyperplane. So I can fold here. Like the result you see is facing the sun here. So that will be a positive fold. So I have an opportunity to fold. Notice I did not fold the first step. It remains and it remains. But the second step, I'm like, yeah, I'm going to fold now. That seems good. And so when I fold, all that happens is that I look at that corresponding hyperplane and I just reflect everything else beyond it across that hyperplane. So all of this bit here, blah, 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 just gets folded, just gets reflected, blah, blah, and the result is that at one spot there becomes a little fold in there. And then I can do this again, and I'm like, yeah, why not fold the next guy? Sure. So I just decided, this hyperplane, I'm going to fold the rest. And it goes blah, blah, and it ends up somewhere else. And that fold is permitted because it's facing the sun. It's a positive fold. And then I didn't fold anymore. Okay, so that's an option. In the statements, you have to like do this in all possible ways. Okay, like all possible ways of creating a positively folded alcove walk that starts at a certain place and ends up at a certain place. So I'm just showing you one example, but in general, you're like running through all possibilities. You or a computer. Can it cross itself again? Oh, probably it can. Yeah, I don't, I've now made my life more interesting by not always caring if the walk is minimal. So I feel like probably this can happen. Maybe if the walk is minimal, it like can't, but I've never thought about that. But somehow minimality feels like it might save me from double crossing. But yeah, I kind of don't really like care about like the details of the image of this pile that's forming. That makes sense. Okay, so I'm just going to give you a notation so I can state a result, and then we can put it to work in some Schubert calculus. So A0, X, Y. So I'm taking now, here's where I'm going to be looking at two Schubert cells, an X Schubert cell and a Y Schubert cell. So you pick two affine Weyl group elements, X and Y, in the beginning. And then you decide on an orientation. So I've chosen an orientation for us of putting the sun in the identity alcove. That's this A0 red. And I'm going to throw into a set all of those labeled folded alcove walks such that you're folding a minimal walk that initially it walks to X, but once it's folded up, it lands on Y. So that's where the two different Schubert cell indices come in. And then it's positive with respect to putting the sun in the base alcove. And then this is just a small piece of some joint work with Kaisa Taipale, which is just to formalize like putting this combinatorics of those particular folded alcove walks in bijection with these particular intersections of affine Schubert cells, an affine Schubert cell and an opposite affine Schubert cell, if you wish. Okay. It does. Yeah. Paves the Richardson. And again, it's a good opportunity to just remind you, if you just want to see a BWB and a B minus VB there, then you do the exact same thing, except you are only looking, your world is just confined to this little hexagon. Well, otherwise you do the exact same thing. So, yeah. Do you remember authors? Oh, Deodar's paper. Oh, I haven't been reading that paper of Deodar's recently enough to say. Does somebody else know, actually? Because you've looked, yeah, the question is maybe you've read this paper recently of Deodar's. So there's a paper of Deodar, a finer decomposition of something. Yeah. Okay. The short answer to the question is that literal paper I haven't looked at recently enough. However, maybe I can make a comment because there's a different paper, Deodar's, that I will say something about, and it might be that one built on the other, and I just didn't look back at the seeds, if that makes sense. Yes, I am. No, I am not going to explain that, but that's what, and also I'll say the details of the proof are only so enlightening because it's inductive on the length of X. And so you can, from the proof, you can figure out what you have to do to increase your length by one little SI or whatever, and the relations and how that changes your coefficient. But the short answer to your question is that it's actually kind of a mess to do. Yeah. Yeah. But yeah, so this is like an it can be done sort of statement. Yeah. I thought rather than go into the details of this proof, I actually thought maybe for this audience, I would show you something Schubert related that this machinery can apply to. So let me give you one. I don't know that you did any GKM theory in the workshop, so I will just give the one-line summary of GKM theory for the affine flag, which probably, if you did some GKM theory, wasn't your context, but anyway. So there are special Schubert classes for the affine flag variety, just as there are for the finite flag variety. I'm sure you've studied those this past week. Here I'm going to not build, but sort of give you a way of thinking about the torus equivariant cohomology of the affine flag variety. And here I actually am working with the really big torus, not the small torus. So that's for comment for the experts. But basically, if this is the first time you're either seeing anything GKM related or you thinking about anything having to do with a cohomology of an affine flag, then I just want to highlight that there's a trade that you can make for a Schubert class to the torus fixed points inside of that same cohomology theory. And these zeta v's, the nature that they have is they are polynomial functions, polynomial valued functions on exactly this affine Bow group that I've built up in alcoves for you so far. So I have a polynomial function that eats an alcove and spits out a z coefficient combination of a bunch of symbols, alpha 1 up to alpha n minus 1 and delta, whatever. These are formal symbols for those of you who don't know what they are, and those of you who know what they are, you know what they are. And the theorem of attributed to Goreski, Kotwitz, McPherson often. Also I would add Costa and Kumar to the mix, and I think it has a rich history, is that the ring structure of this torus equivariant cohomology is completely determined by the pointwise product of these polynomial functions. So if you understand how to make a trade over to the functions, then you multiply polynomial functions, and you can do the same Schubert calculus. Okay, so it's a trade for something more algebraic. All right. So what I want to give you as an application of this story is how to actually think about these functions, which are under this like inclusion. These are, I mean, and it's actually an isomorphism onto its image. So these are the Schubert classes, for lack of a better way of saying it. These polynomial functions are the affine Schubert classes. Let me explain to you how to think about those functions in the ways that I've set up. Okay. Super crash course. All right, so I want to tell you how to compute their values. So fix a v in your mind. This is going to be the polynomial function representing the affine Schubert class corresponding to v. And I just want to compute its value at another w. So fix another alcove w in your mind. Could be the same alcove, it could be a different one. Here's what you do. And basically the big thing that I need to do in the beginning is, okay, first of all, sort of awkwardly, actually, where you are evaluating this polynomial function, that's where you take a walk to. So I have to fix w and walk to w. And I'm just choosing a word for w here. I'm choosing S1, S2, S1, S0, whatever. So here's a walk, 1, 2, 1, 0. There I am, right there. And I just along the way, kind of in preparation, just want to note the hyperplanes that I crossed. That turns out to be the important data for evaluating this function. So which did I cross first? I crossed here first. This is like whatever. I didn't tell you how to index these hyperplanes properly, but this is the hyperplane indexed by alpha 1. Then I cross this one. That's the hyperplane indexed by alpha 1 plus alpha 2. Then I cross this one. That's the index by alpha 2. Then I cross this one. It's parallel to this one. So it's actually indexed by the same initial bit, alpha 1 plus alpha 2, but it's like one further away from the origin, so it's plus delta. Okay. So I've just noted the hyperplanes that I crossed for this setup minimal walk. All right. But then what I do is now I think about, okay, what Schubert class are you trying to deal with? So now I'm fixing a v. So I just chose S1, S0, whatever, okay? And I think how many ways can I form a subword of the initial w, which is equal to the word, the element v, okay? And I can do it in two different ways. It just so happens in this example, okay? So let's see. So what could I do? I could omit, keep. And then I would have S1, S0, right? So that omit, keep will turn into fold, step. It's just the word omit turns to fold and the word keep turns to step. And so what am I supposed to do? I'm supposed to fold, let's see, whoops, I have fold here first, then fold here, and then step, and then step. So this is like now a folded alcove walk. First the pink, then the orange, then this step, and I land over here, and I land on V. This is the S10 alcove over here. When I did each of those, yeah, what do I want to say? the steps, this is where you have to do one thing, go back to the original setup. So those steps, those step and the step here, they correspond by color to these two, like, collections of whatever, these two polynomials. Those were indexing the crossings corresponding to those two steps in the original. So there's like this reference to the original that's happening. The last two steps here and here are the alpha 2 step and the alpha 1 plus alpha 2 plus delta step. So yeah, but that's just is what it is. Okay. So you record the hyperplanes indexing those steps which remain, but you record the hyperplanes from the original walk to W. And then you do this in all possible ways, i.e. form V as a subword of W in all possible ways. When you've got a step that remains, check where it came from in the orig, record. Okay, that's the process. And then I would get this collection of polynomials in this case. So step, fold, fold, step. And so this is a version of Billy's formula, what many of you may know as Billy's formula, is that if you fix a pair of affine vowel group elements, B and W, take actually any unfolded walk that you want to W. So you don't have to be minimal, and this will still give you the right localization. So you could just walk however you want to W, and then you look at all of those folded walks which end in V. And you record products of the steps from the original walk. And you sum all of those up, and that will be the polynomial value for the Schubert class indexed by V at the torus fixed point W. This is, yeah, so this is just what that example, we just did these two calculations one by one, and this is just like putting it into that notation, is that we have computed one value of the Schubert class, the affine Schubert class S1, S0, at a particular alcove or a particular torus fixed point. And this is how the sum collects in that case. All right. Okay. So I don't have, this is the paper of Deodar that I was mentioning. It just so happens that the exact same example also computes an R value for you, an R polynomial for you. And this was already known to Deodar in like not this language, but like worked out in more or less this exact way. I don't remember which paper I'm referencing of Deodar, but somehow if you record just slightly different data, I should emphasize here in the previous, whoops, here we go. In the previous formula, this localization formula here, I actually didn't care about positivity. You just fold in all possible ways land on V and record those. It doesn't matter if they're positive or not. If you want to compute an R polynomial, now you restrict to just the class of folded walks where all the folds are happening on a positive side. And you record some statistics for that walk. How many folds does it have and how many positive crossings does it have? But I think it certainly is in there. I can't remember. It may be actually that bit of this paper that you're referencing, Alex. Right. Yeah, so I've looked most recently at the Kazhdan-Listig polynomial one. And this statement, not in this way, but this statement is in there, but it's from an earlier paper, and it's probably exactly the one that Frank is referencing. Yeah. So I don't have like any more time, but I just want to say, yeah, okay, right. So I just want to say that in the literally exact same example that we just did computes also in our polynomial for the same pair, W and V, right? Except that you just have to pay attention to, were those folds against positive sides or were they not, if you're doing an R polynomial calculation. So this example, we had 2 positive folds. I can't do left hand. Yeah. This is towards the sun, so those stay, but this one has a non-positive fold. This orange fold is on the opposite side, facing away from the sun, so it would get trashed in the R polynomial calculation. And then I've recorded the statistics. How many folds did I have? I folded twice, and I would have to tell you I can tell you how to compute whether a positive crossing is just a step towards the positive side, like from the negative side of a hyperplane to a positive side. And we took none of those in the previous examples, so we haven't seen examples of them, but here's how that R polynomial looks then. Just like doing nothing different, basically. So I think, yeah, okay, yeah. I think before you clap, I just want to say, this is another example of a story you can tell using the same tools, but I will let you like muse over that and take your questions now. Thanks very much.